Okay, so this last part here, we're going to do solution stoichiometry, and we're going to do it with titration. And we're going to do a lab. Obviously I can't do labs, but we'll do some lab data, and you can pretend you're doing it. But titrations involve the neutralization of an acid with a base. And they can be more complicated than the ones we're going to do. We're just going to do a strong acid, strong base. It's pretty straightforward. When we neutralize, we have a pH of 7. We're going to fill a burette with a certain concentration of sodium hydroxide. And I usually say the burette has the base in it, NaOH. That doesn't have to be that way, but often it is. So let's say that we're going to fill this burette with a known concentration of sodium hydroxide, 0.34 molar. And then what we're going to do is put 15 milliliters of hydrochloric into the flask. We're going to add a drop or two of phenolphthalein. Now, it will be colorless in the acid, but as soon as the sodium hydroxide neutralizes the acid, the solution will turn light pink. Now, I have a couple of videos for you to watch as part of your lab, and so you'll see a video of this as well, and I definitely want you to watch that, see what it is. If we can't do labs, at least you can look and see how you do the lab. Okay. When it turns light pink, not dark pink, but light pink, right at that point when one drop turns light pink, the correct number of moles of acid and base have been reacted, and the solution should all be water and NaCl. You could literally drink it. I wouldn't ever drink that because phenolphthalein is a known laxative, but it's a little bit toxic. But other than that, the water and the NaCl, it should be fine to taste it, for instance. Let's say that it takes 52 mils of sodium hydroxide to neutralize the 15 mils of hydrochloric acid. What would be the concentration of the HCl? Okay, so let's take a look at this. So we have this set up here, and what's happening is in the burette, we're putting the sodium hydroxide. And by the way, the ink color that I'm using is really what the color of phenolphthalein turns in the presence of sodium hydroxide. But what we're going to put down here is we're going to put the acid down here and in here, and we're really careful when we measure this out. This is one of the ones we're really careful on how much we add. So we add a little, we take a pipette or a little graduate cylinder, we put exactly 15 mils in there. We rinse out the measuring device because we want exactly 15 mils. We don't care if there's more water in here, that's fine, but we want exactly 15 mils of hydrochloric acid. Okay, we are trying to find the molarity of hydrochloric acid. What's the concentration? This is used a lot in environmental labs too, to find the concentration of a pollutant or a contaminant in groundwater. Different kinds of titrations are done here. But let's say we know that this is 0.34 molar, like I mentioned on the previous page. And what we do is we start with a certain amount, we read it, we add this, it comes down, we add this until this right here just turns a light pink throughout, and we swirl the entire time. Again, watch the video on how this is done. But then we end it, once this turns light pink, we end it, and then this amount right here, we measure. So this will be the initial volume, the final volume, we subtract those two. And let's say that when we do that, it takes 52.0 mils of it to turn this solution light pink. All right, so how this is done with solution stoichiometry then, we did a problem in the last video where we had to find the volume. And in this one, we're trying to find the concentration. So we need to know the molarity of the hydrochloric acid, and we've used exactly 15 mils. And again, this is really important to keep track of when you're doing the problem or doing the lab. And we used 52 mils of sodium hydroxide. Generally what happens if we were in school, we'd be doing this. And I would have you run at least 3 trials of the same amount. So run this 3 different times, take the volume, average all 3 trials, and come up with that average. All right, so once we have that data, again, we're going to start this. We're going to start with the concentration and volume of the thing we know, which is sodium hydroxide. And again, the most common problem I see is people not keeping track of what you're talking about, so that's why this is helpful. Well, we're going to take 0.34 moles per liter. We're going to multiply by 0.052 liters. Right? We want to change that to liters. That cancels, and we're going to get 0.0177 moles of sodium hydroxide. Now, in our lab that I'm going to have you guys do, this is going to be H2SO4 sulfuric, so we will have a 2-to-1 ratio. Again, with my example, it's pretty boring 1-to-1, but it is important to follow that protocol. I would say the other common mistake is people try to use like the dilution formula or something because it's 1-to-1. And that does work if it's 1-to-1, but not if it's 2-to-1 or 2-to-3, or you get it, the idea. All right, so do the stoichiometry and we get 0.0177 moles of hydrochloric. So these two steps are the same with any solution stoichiometry problem. It's the third step that's a little bit different. Sometimes we've been asked to go to grams. In the last example, in the last video, you were asked to find volume. You were given a molarity and you had to divide by that molarity and got volume. In this case, we are asked to create a molarity. Now we know this many moles are in 15 mils, so all we're going to do is put those two pieces of information together, moles over liters, and get a molarity. So the molarity here is going to be, I take that 0.0177 moles, I'm going to divide by 0.015 liters. That comes from this 15 mils, but I change it to liters. And I will calculate the molarity of the hydrochloric acid. So if you were doing this in lab, it's a 2-day lab, and I actually grade you on how close you come to the right answer with your calculations. But all right, let's try one other problem, which will end our solution notes because, well, we'll talk briefly about molality at the end here, but we won't do anything with it. All right, so we have another equation, H2SO4 sulfuric acid, which is going to be aqueous, of course, and sodium hydroxide, which is going to be aqueous. And we're going to do that the titration, and we will come up with sodium sulfate, which will stay aqueous, and we will have water. Okay. And so we are now going to have a balanced equation of 1 to 2 to 1 to 2. All right, so it says, what is the concentration of sodium hydroxide if 35 mils of it neutralizes 62.0 mils of a 0.5 molar solution of H2SO4? So again, the first couple of steps are the same in all of these. I'm going to take this, multiply by 0.062 liters. And when we multiply that, get 0.031 moles of H2SO4. All right. We're then going to do the stoichiometry, which is 1 to 2. 1 mole of H2SO4 requires 2 moles of sodium hydroxide. So we're back to 0.062. All right, so we then have to figure out the concentration. We have a volume. We have moles. We're going to take those two pieces of information and put them together because we know that 35 mils or 0.035 liters contains that many moles. And what we get is 1.77 molar sodium hydroxide. All right. So those are any of the things you see on the worksheets are going to be a variation of one of those. So check back on the video if you're stuck at where to go. But the first two steps are going to be the same. You're going to take your molarity, your volume, make sure it's in liters, get moles, do your stoichiometry, get moles of the thing you're being asked about. The third step will be different. Sometimes you'll be asked about grams. Sometimes you'll be asked to take this, divide by the molarity if it's given to you and get liters and then mils. Or sometimes you'll be asked for molarity and given mils and you have to do this. So those are the three variations really. The last thing I'm going to mention is molality. And the only reason you don't have to be able to calculate molality, it's moles of solute over kilograms of solvent, which is a little bit different. But I have a little cursive M there. But the biggest thing I want you to realize once we have the molality, which we could calculate, is that a colligative property, and this is why we're doing, or we would do molality, is that when a solute is dissolved in a solvent, the resulting solution will freeze at a lower temperature and boil at a higher temperature than the pure solvent. And we know this in Minnesota more than anyone because we put salt or we put calcium chloride out on the sidewalks and the roads because we don't want the water to freeze. We would like it to not freeze at 0 degrees Celsius. We'd like it to lower. At some point, there's just not enough salt in the world to put down. It just gets too cold. But this does work to lower the freezing point, and then we don't have ice on the roads. It does boil at a higher temperature too, so if you put salt in water to boil pasta, it's going to take a longer time to boil, but it will be boiling at a hotter temperature, and so the pasta would cook more quickly there. The other thing to mention here and think about is that when we have an ionic solute, we actually look at the different ions, and a 1 molar solution of NaCl will actually have a 2 molar effect on the freezing and boiling point because we have Na+1 and Cl-1, so double the power. It's actually just a physical blocking thing that happens here. Calcium chloride would have 3 ions. It would have a calcium +2, a chloride -1, and another chloride -1, so it would actually have triple the effect. Now there is a point of diminishing returns there. If you tried to do something, that would break into like 5, 6 ions, you do get a diminishing returns there. But calcium chloride is definitely a better thing to put on your sidewalk than NaCl because it has triple the effect than something that isn't ionic. It does cost more as well. So that's all you really need to know about colligative properties. You will be asked about that. You can actually calculate how much the freezing point will depress, how much using something called a K constant and multiply it by the molality of the solution. But again, we're going to try to keep it simple for the rest of the year and not do that. The other thing I will mention, you could do boiling point elevation too. The other thing you can do with this is calculate the molar mass of something. So just as a recall, we did empirical formulas, and then we said, okay, well, what's the true formula if the molar mass of the true substance is this? Well, this is one way of several ways you could actually calculate the molar mass of something, an unknown. Okay, so that's it for this last video.